Hello, pre-calc. Check it out. There's spinners. One fish, two fish, red fish, blue fish. Cool. Well, a local market, which will remain nameless, has a promotion where they're giving away free fish, like to eat, not for pets. Customers get to spin 2 spinners. You see them in the picture there. There's a blue one and the green one. They're called the Wheel of Fish. And that determines the number of free fish that they get. And you have been selected as the daily double spin winner. Woo! But you do have a geeky math teacher, and let's just say that your geeky math teacher planted this idea in your mind and you just can't get rid of it. And now you start wondering, what are all the ways that a double spin winner spinners could spin? List them. Big list. Also, in addition to just the combinations of spins, give me the total number of fish. Also, please. And it'll take you a minute or two. Go ahead and hit pause until you have your list completed. Hey, welcome back. I'll put links to these videos here in the Canvas page, just for fun. If you had that many fish, there's maybe too many to eat. You might need some ideas about how you could deal with all those fish. This video will give you some ideas. All right, well, I pulled a fast one on you with the list because I made my list in a totally different format than what I suggested to you. And there's not a right or wrong. Make your list however you want. This is called an outcome table. It's got 2 axes. So I put all the outcomes for the blue spinner on the one side, all the outcomes for the green spinner on the other side. And then each cell in my table just represents a possible combination. So I could have got 4 on the blue spinner and 1 on the green spinner, and that would give me a total of 5 fish, right? And so I can see just by the location on the table, the combination is 4 on blue and 1 on green. And then the number 5 tells me the total possible numbers of fish that I win. Some advantages to making a table this way are, 1, you can very easily determine how many total outcomes are possible. What's the total number of different ways you could, a double spin winner spinners could spin? It's 25, right? Because the little square is 5 by 5. Okay, well, let's see, that's pretty easy. You could have figured that out anyway. But another advantage is you could easily answer questions like this one. How many different double spin outcomes would award you a total of 5 fish? Well, there's 4 spots in my outcome table that give me 5 fish, right? 4 and 1, 3 on blue and 2 on green, 2 on blue and 3 on green, 1 on blue and 4 on green, and there they are. 4 outcomes give me 5 fish. All right, well, today we're going to continue our intro to stats, or fish statistics, as I like to call it, fish statistics. Because fish, learning target is unchanged from yesterday. You'll be able to use counting methods to find probability. Of course, there's that overlap between probability and statistics. So really our goal here is statistics, but lots of probability is going to show up along the way. Counting methods. All right, well, we just saw another one. An outcome table is a counting method, and we can make outcome tables in lots of different, shapes and sizes. And that is our first strategy of the day. Outcome tables. Okay, let's refer back to a couple of things from yesterday because there's some Easter eggs. We want to uncover them. So you remember this table you made from yesterday? It's still in your notebook, hopefully, because you're keeping all of the outcome tables and other sorts of things we're doing in class and do nows and stuff. Keep them for future reference in your notebook. Here's the outcome table for 3 coin flips that we did yesterday. And let's look at some different things here than what we did yesterday. So out of the 8 total outcomes, how many of them give you no heads? Right? Well, I already answered this one. To get no heads, the only possible way for that to happen is if you get tails on all 3 of your flips, right? So I highlighted that in yellow. There's 1 outcome that gives us no heads. Now, I'm going to fill in some more numbers here. If I got no heads, that means I got 3 tails, right? Because there were 3 coins. If none of them are heads, all 3 of them are tails. So no heads goes with 3 tails. It's the same number of outcomes. It's the same question, whether I say how many ways could you get no heads, how many ways could you get 3 tails? This is like, change the words. It's the same question. Okay, how about how many ways are there to get 1 head? Right. Well, I've already answered that one. It is three ways. They're circled there in red in the outcome table. You could get tails, heads, tails, 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 heads, or heads, tails, tails. Okay, so there are three of those different outcomes. And underneath one heads, another way of saying the exact same question is, how many ways could you get two tails? Right, because there's only three total coins, and if one of those coins is heads, the other two have to be tails. So one heads, there's three outcomes. Two tails, same question. Also, three outcomes. All right, well, what about two heads? How many different ways could we get two heads? Give you a minute to look. Two heads, two heads, two heads. There are three outcomes there. If you think about the coins, if there are two heads, the other coin would have to be tails, so one tails. How many ways could I get one tail? Well, those same three outcomes give me one tail. And then last one, how many ways could I get three heads? Well, there's only one outcome that does that. And another way to say the same question, if all three coins land on heads, that means none of those coins landed on tails. Here's the question. How many ways can I flip three coins and get zero tails? Well, there's one way. I circled it in blue. All right, pay attention to these numbers. 1, 3, 3, 1. Those are called categorizations. So we've got our whole outcome table that lists all the possible outcomes. We can categorize them or subcategorize them, might make more sense. So instead of just saying, here's all of the outcomes, look, some of us give us different quantities, right? The order of the flips might have been different, but there were three outcomes that fall into the category of giving us one heads, right? Or maybe you're playing a game where if you land on heads, you win. So we might say, look, if you play this game, you get to flip the coin three times. You do the experiment with three trials. How many possible outcome combinations would give you success one time exactly? Right? Well, three. There are three outcomes that give you the one heads. Okay, so categories. Also yesterday, we did this binomial expansion. We multiplied t plus h to the power of 2. Let's focus our gaze. And when we multiplied that out, we got t squared plus 2th plus h squared. I asked you yesterday to identify the coefficients, 1, 2, and 1. Then I asked for some more multiplication. We did t plus h quantity to the power of 3. So we took that previous answer, put that on one edge of multiplication box, multiplied by t plus h one more time, collected like terms, ended up down here, t to the power of 3 plus 3 t squared h plus 3 t h squared plus h cubed. And I asked you yesterday to identify those coefficients, 1, 3, 3, and 1. Those seem familiar, those numbers, that pattern, 1, 3, 3, 1? I hope so, because we just saw it right here. It's the same as these categorizations that we saw from our outcome table of doing 3 coin flips. Oh my gosh, there's hidden meaning. What do you suppose the T and the H might represent? It's tails and heads, the two outcomes for a coin flip. What do you suppose this 3 might represent? It's the number of trials of the experiment of flipping a coin, which has tails and heads as the possible outcomes. And then the coefficients give us the number of outcomes in each category, and the variables actually give us what those outcomes are. T to the power of 3, that's going to represent tails on all 3 coins. There's one outcome. The coefficient tells you the number of outcomes. The variable and its exponent tell you the specific quantity, the label of that category. Next term, t squared h. That would mean 2 coins landed on tails, 1 coin lands on heads. The coefficient tells you the number of outcomes that are in that category. 3 different ways to get tails on 2 coins and heads on the other. 3 different outcomes give you tails on 1 coin and heads on 2 coins. And then lastly, there's 1 possible outcome where you get heads on all 3 coins. Wow. You didn't see that one coming. Right. So here's what we need to write into our notes for today. On the left-hand side, we saw that yesterday. To determine the size of a sample space, we can use an exponent, a base and an exponent, to calculate the size of the sample space for a repeated event, right? So the base number is the number of outcomes for each individual trial. So if it's a coin flip, 2 sides, base is 2. The exponent is how many times you repeat that trial or repeat the event. So 3 coin flips, the exponent will be 3. That will tell us the size of the sample space, just the number of outcomes. But if we want to get the actual sample space, so we can use some algebra to accomplish that, maybe you'd say, yeah, I see where you're coming from, but that's a lot of work. Possibly true. But still, we can get the whole sample space this way. There are advantages. Possibly time it takes to calculate a binomial expansion may be a disadvantage. There could be some ways around that. We'll see. So inside the parentheses, that represents the outcomes, not how many outcomes, but the actual outcomes. So a coin has 2 outcomes. So inside the parentheses, I'm going to list them both, H plus T, in the algebraic form. So heads for A is the H, tails is the T. Put a plus to separate your 2 terms in that algebra expression. The exponent is still going to be the same. If I'm doing 3 coin flips, I'm going to make that exponent a 3. That's the number of repetitions of that event. This is called a polynomial model. Super important tool. We're going to learn some more about in the coming days. Super important statistical tool, polynomial modeling. All right. Another super important tool is Pascal's triangle. I don't know if you've learned about Pascal's triangle in previous classes. So named after Blaise Pascal, a French mathematician several hundred years ago, he came up with this pattern. And as it turns out, it has like an infinite number of different applications in math. And so, well, that's an exaggeration, but there's a ton, right? And way, way more than what he ever expected there would be, just like applications every which way. Okay, so I'll explain where Pascal's triangle comes from, how you can create it for yourself, what the pattern is. But oh my gosh, look, there's those same numbers again. 1, 3, 3, 1. Those are the numbers that describe the number of outcomes in each of the categories for 3 coin flips. Okay, and to be fair, Pascal's triangle is not only referring to coins as a nice example for us, but any kind of event, any statistical experiment which has 2 outcomes. It could be heads and tails, it could be a win and a loss, a yes and no, I mean, whatever. Okay, just anything with 2 outcomes. If I go up 1 row, 1, 2, 1, those are the number of outcomes that describe, or the number of outcomes in each of the categories for 2 coin flips. There's 1 possible outcome where you get no heads. There are 2 different ways where you could get a head on a single coin. You could get heads, tails, or tails, heads. So there's 2 outcomes there. The last one, there's 1 outcome where you get no heads at all, right? This is the number of outcomes in each of the categories for 2 coin flips. For 1 coin flip, there's 1 outcome that gives you 1 heads. There's 1 outcome that gives you no heads. If you had no coins at all, well, there's only one way to have no coins, and that's to not have them, right? As far as the statistical experiment, what could possibly happen? There's only one thing that can happen, and that's there is no outcome. Because there is no coin, you can't flip it. Okay, so we can extend this pattern. If we knew what the pattern was, we could extend it to do more coin flips or more repetitions of this 2 outcome event, heads, tails, yes, no, win, loss, whatever the 2 outcomes are. Here's how Pascal created the pattern. So the top row is called the 0 row, or row 0, because it represents, in our case, having no coins, even though you can't read the word that I wrote here. And so the 0 row, but it has 1 element in the row. Okay, each succeeding row is going to have an additional element. So there's 1 element here, 2 elements, the 1 and the 1, for a total of 2 things. I think I'm going to write these in the other. It makes more sense. Row 1, row 0. Okay, so the way you get each next row, so there's an additional element. The left and the right numbers will always 1. 1 at the left side, 1 at the right side, and then you add together the two numbers, the adjacent numbers in the preceding row. So 1 plus 1 gives us 2. That's that middle number. 1 plus 2 gives us 3. And over here, you could repeat the use of numbers. So that same 2, but plus the other 1 on the other side. 2 plus 1 is 3. That gives us the other 3 right there. And then that pattern would continue. A 1 at the beginning, the 1 and the 3 in the previous row. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then you get a 1 at the other end, and that would be row 4. So the row number describes the number of coins. So this would be 4 coins. If we categorize them, there's one outcome that gives you 4 heads. There's 4 different outcomes that give you 3 heads. There are 6 different outcomes that give you 2 heads. There's 4 outcomes that give you 1 head, and there are one outcome left that gives you no heads. Always in that order, right? So the second number in the row describes the row number or the number of coins represented by that particular row. All right, so if you had a copy of Pascal's triangle, which you should have and keep in your notebook, then we can answer questions like this. When you flip a coin 5 times, there are a possible blank number of outcomes. All right, well, before we get to Pascal's triangle, let's figure this out. If you flip a coin 5 times, how many possible outcomes are there? Well, we can calculate the size of the sample space by using that exponent, right? How many sides on a coin? How many repetitions of the trial? So I'm going to do 2 to the power of 5, multiply, multiply, multiply. That's 32. So there are 32 total outcomes. How many outcomes are in each category? So if you're flipping 5 coins, what are the categories? You could get no heads, you get 1 head, 2 heads, 3 heads, 4 heads, 5 heads. Those are the categories. I have them labeled there. Okay, so we're going to go with Pascal's triangle. We'd want to find the 5th row. Remember, Pascal's triangle always starts at row 0, just like the assignment numbers in the statistics unit. We started at day 0, and today will be day 1. All right, so row 0, row 1, row 2, row 3, row 4, row 5, or the second number in is a 5, right? Okay, those numbers in Pascal's triangle represent the number of outcomes in each category in the order that I have them listed. So at the one edge of Pascal's triangle, that's not a pen. That's going to be 0 successes. And whether you call it getting heads success or tails getting success, it doesn't actually matter. It's the same either way. You'll notice the numbers in Pascal's triangle are symmetrical from left to right. So there is 1 outcome in the 0 heads category, 5 outcomes in the 1 heads category, 10 different outcomes in the 2 heads category, 10 again in the 3 heads category, 5 outcomes in the 4 heads category. 1 outcome would give us 5 heads. Let's try another one. What if you flip a coin 8 times? There's a total number of how many outcomes possible? Think time. 2 to the power of 8, which is a large number. What is 2 to the power of 8? Yeah, I don't have my calculator handy. That was 250, 512, 256, 2, 4, 8, 16, 32, 64, 256. Okay, how many outcomes are in each of these categories? 0 heads, 1 head, 2 heads, 3 heads, 4 heads, 5 heads, 6 heads, 7 heads, 8 heads. Okay, well, I have to go to row 8. Oh, no, it's not there. All right, well, fortunately, we know how Pascal's triangle can be created. Because we got that pattern, we could add together to get some more rows. For example, also there's another way, which we'll learn tomorrow, where you don't have to actually create all of Pascal's triangle. But for today, we'll just keep adding here. So I'm going to have a 1 at both ends. Okay, The 1 and the 6, that makes 7. Add the 6 and the 15, that's 21. 15 plus 20, 35. 20 plus 15 is the same thing, also 35. 15 plus 6 is 21. 6 plus 1 is 7. Next row, I'm going to have a 1 at the beginning. I'm going to have a 1 at the end. It's going to be a little bit wider because I have one more number that goes in this row. Add 1 plus 7 is 8. 7 plus 21 is 28. 21 plus 35 is 56. 35 and 35 makes 70. And then the other side is going to repeat the same numbers. 35 plus 21 is 56. 21 and 7 is 28. 7 and 1 makes 8. That green row is the answers to this question up here. How many outcomes are in each category? 1, 28, 56, 70, 56, 28, 8, 1. Okay, so I'm going to remind you again, keep all of this work in your notebook because you will have many opportunities to refer back to it. It's going to save you some work. Like, for example, the table of outcomes with the 5 fish and the 5 fish on the 2 spinners is going to show up later in the assignment. And probably again in a couple of days. Pascal's triangle, absolutely, definitely. Probably you're going to want more than 6 rows. Although, to be fair, we'll also learn a way where you will be able to find those specific numbers in Pascal's triangle without having to look at the exact triangle every single time. But you should still have a copy of it in your notebook.